Okay, today's lesson is on thermochemical equations. In the last couple of lessons, we learned how to calculate the enthalpy using calorimetry, and we dealt with physical changes as well as chemical changes. And in all of these cases, we have come up with a certain amount of energy, a certain number of joules that is produced during a chemical reaction. In this lesson, we will learn how to systematically put those energy values into a chemical equation so that we can represent it as a complete chemical equation and not necessarily as a mathematical problem that we did in the past. So we want to be able to incorporate this energy information that we've now obtained from our calculations in a chemical reaction. So what is a thermochemical equation? Well, it's a regular balanced chemical equation, but it indicates the amount of energy that is absorbed or released in the chemical reaction. All right? So it's really, we're just adding the energy term onto a balanced chemical equation so that we can make sense out of it. Now, there are four main ways in which this can be done. Now, I'm going to go through this quickly. Again, the teacher can pause this so that you can write it down, or perhaps you can get it off of the PowerPoint later on. So in order to illustrate this, we're going to use photosynthesis as an example. So in a photosynthesis reaction, 6 carbon dioxides react together with 6 waters to produce a glucose molecule and 6 oxygens. And in photosynthesis, you may recall from your biology class, energy is taken in the form of light. So this is an endothermic reaction. Energy is put into this chemical reaction. The opposite of photosynthesis we call cellular respiration. That's when a glucose molecule reacts with oxygen to produce carbon dioxide and water, and energy is given off. Right? That energy is used by the cell or by whatever excuse me, part of the cell that is going to use that energy. So we're going to use these two reactions to represent these 4 different methods. So method number 1, we put the energy term right in as part of the chemical reaction. All right? So you can see here that we've got the allotted amount of energy that is absorbed for 6 carbon dioxide molecules and 6 water molecules to produce 1 glucose molecule. And because it's endothermic, we put the energy in as a reactant on the reactant side. All right? And so endothermic reactions are put in as a reactant. You can see there down there on the bullet. If we talk then about cellular respiration and we flip the reaction over, you can see here now that our energy is represented as a product. So in the past, we've represented an endothermic reaction as a positive delta H. In this case, there's no sign and we put it in as a reactant. And an exothermic reaction is a negative delta H, but again, in this case, there's no sign, but it's represented in as the products. All right? So if energy is a product, it's exothermic. If energy is a reactant, it is endothermic. All right? Again, fractional coefficients are acceptable. In this case, we don't have any fractional coefficients, but it's kind of like our stoichiometry. If you happen to have a fraction in there, it's okay. All right. So part 1, energy is part of the chemical equation. Method number 2. We're going to take that energy out of the equation, and we're going to simply put it as a delta H term on the back end. All right, so there you can see I've put that delta H term on the back end. This is separate from the chemical reaction. So here again, we've got our chemical reaction. We write it down, and then we put a delta H value on the end. Again, because it is endothermic, photosynthesis is endothermic, we have a positive delta H, and we don't write the plus in there like we normally don't. So positive delta H is endothermic, and we already knew that. Again, cellular respiration, we flip the reaction over, And now, again, our delta H term that we put on the end, you don't have to put boxes around them. I'm just doing this to highlight it. And you can see here, we've got our negative value, and that is representing exo. So positive delta H is endo, all right, endo, and a negative delta H is exo. So that has the delta H term separate from the chemical reaction, just put in behind, all right? And the last one is written as a molar enthalpy, all right? Now, you really don't need to rewrite this because I'm writing the same stuff, but now I can represent it as a molar enthalpy on its own. You can see there, and you can see here I've got delta H now again with my subscript photosynthesis. And the only difference is now that I put my kilojoules, but I must have a per mole, and in this case, I have to indicate it to what it's per mole of. Now, if I go back up to this chemical reaction here, you'll notice I've got 6 carbon dioxides, 6 waters, 1 glucose, and 6 oxygens. So to take this out as a molar enthalpy, because the coefficient right there is 1, then I can state that this is a molar enthalpy of 2,802.7 kilojoules per 1 mole of glucose. Excuse me again. I could have done it per mole, all right, if I did photosynthesis, per mole of oxygen, but if I do it in terms of per mole of oxygen, I need to divide that number there by 6, because this is 6 oxygens. So if I get my calculator running, 2802.7 divided by 6, that gets me 467.1 kilojoules, but now it's per mole of O2. So I could represent it as different reactants or products, but I might have to do a little bit of math to figure out the ones that do not have a coefficient of 1. If they have a coefficient of 1, then the molar enthalpy is the same as the regular enthalpy divided by 1. All right? So same thing for respiration. We're flipping it over. We've got exothermic. It's negative. The delta H for cellular respiration is negative 2802.7 kilojoules per mole of C6H12O6. So all we're doing here is we're representing it as a per mole of one of the reactants. Notice here, just as before, this particular molar enthalpy can be used as a conversion factor, all right? That type of thing is going to convert kilojoules to moles, in this case, moles of glucose, all right? We can use it to convert back and forth. That's some calculations that we might want to do. All right, the last way in which we represent thermochemical equations, and that's with a graph. Whoops, get that thing out of the way. So that's with a graphical representation. So all we do is we draw a grid, we write potential energy up the side in kilojoules, we've got reaction progress. We don't really have a time or an x-axis. It's just how, as the reaction progresses from reactants to products. And here, we're not even putting a grid on the side of potential energy. We just want to represent the fact that we're increasing in enthalpy, it's endothermic, and therefore our energy is going up. So here we've got our reactants of photosynthesis. The energy value goes up, and we now have more energy stored. It's an endothermic reaction. All right? And if we take a look at cellular respiration, it's going to be the same, except, boom, it drops down. It's exothermic. So this gives us a visual representation of what's happening to the energy in terms of its stored chemical potential energy. All right? So let's do a couple of little examples here. Write the thermochemical equations with the delta H of a reaction to represent each of the following. The combustion of butane, and the delta H of combustion of butane is that many kilojoules per mole. So we want the delta H term, not the molar one, This is the molar enthalpy of combustion. We just want the delta H term. So if we take butane, and I need to tell you what the formula for butane is, and it turns out that it is C4H10 plus O2 to produce CO2 plus H2O. And let's balance this up. 4, 10, 5, and O2s, 4 O2s, and 2.5 O2s, 6.5. And notice that this is a molar enthalpy, which means I need 1 mole of butane in my equation for this to be true, and I do. So I can turn this molar enthalpy straight into just a delta H by getting rid of the per mole, because there is 1 mole here, and that's simply going to be negative 2.871 kilojoules. It's not on a per mole basis anymore for this entire chemical reaction. So what have I done? I've taken this information and I've written it like this, but it's really the same thing. This is telling me for 1 mole of butane, I get 2,871 kilojoules, and this equation says the same thing. For 1 mole of butane, I get 2,871 kilojoules. So I've really just translated it into a different way of writing it. What if I was talking about 2 moles of butane? Well, then I could double all of my coefficients. 2C4H10. Oops, that's not an H. 2C4H10. And now, to keep it balanced, 13O2, 8 CO2, 10 H2O. And if this is for 1 mole, then all I have to do to get the reaction for 2 moles is double it. So get in my calculator, 2,871 times 2, 5,742 kilojoules. Nothing complicated about this. If I want 2 moles of butane, I'm double everything up. I double the energy as well. Okay? All right. Let's look at another example. Same thing. Endothermic reaction that occurs when 1 mole of AgNO3 dissolves, and we've got the heat of solution. What we're really testing you here is on writing a dissolving reaction. AgNO3 solid as it dissolves. Actually, maybe we should put here aqueous because it has dissolved. It doesn't really matter. Aqueous. That's going to get us an Ag plus aqueous plus NO3 minus aqueous. And I've got a 1 here. That's per 1 mole. Delta H equals 2.6 kilojoules per 1 mole. And because I've got a 1 there, I've got it written with a delta H term. It's really very simple. We're just really writing it in a different way. The formation of MgCO3 from its elements. A formation reaction, and we're going to learn more about formation reactions, is a reaction that creates the substance from its elements. So I'm going to start with, because we're going to create some magnesium carbonate, I need to look at each of the elements. And this is Mg solid, because that's how I find magnesium on the periodic table in a solid state, plus some carbon solid, and some oxygen O2 gas. And we're going to form some MgCO3, and that is going to be a solid. And so that's a formation reaction. We are building the compound from its elements in their standard states. And that's supposed to be a gas, not a Q, gas. And let's balance it. 1, 1, 1, 1, 3, 2. So again, I need a 1.5. And if this is negative 1095.8 kilojoules per 1 mole, notice I've got a 1, all right? And therefore my delta H is the same number, negative 1095.8 kilojoules, all right? So a formation reaction, we'll see that again in the future. This is a little quick introduction, is making the compound from its elements and then balancing it so that this number is always 1. The coefficient of this guy on the back end is always 1, all right? All right, let's take a look at a couple more examples. Okay, here we've got now the reverse. Here's our reaction. Determine the delta H for combustion of SO2. So here we've got it combusting. It's reacting with the oxygen. Notice though, we want it per mole of SO2. That's what that little subscript means. Notice here I've got 2 SO2s. So in order to get the delta H of combustion, I'm going to take the delta H and I'm going to divide it by the number of moles. We already know this equation. We already know that the delta H, the molar enthalpy, is equal to the enthalpy divided by the number of moles. We can use that equation here. Negative 197.8 kilojoules divided by 2 moles of SO2. So now we do some calculations. 197.8 divided by 2 equals, therefore it is negative 98.9 kilojoules per mole of SO2. And that makes it a molar enthalpy. All right? So we're not doing anything magical here. We're just using our definitions of molar enthalpy versus enthalpy, and we're using the chemical equation now to get our moles and get the information we need so that we can write it in different ways. Okay, so now let's use this. Let's find the delta H then if we have 2.5 grams of SO2 to react. Now this goes back to our review on stoichiometry. This is where I need you to think in terms of steps. In the end, I want this total delta H, but instead of 2 moles of SO2, I've got 2.5 grams of SO2. Well, eventually I got to get to moles so that I can eventually get to my energy. Which means, if we think about it, we're definitely going to need some moles of SO2. So how am I going to go from 2.5 grams of SO2 to moles of SO2? Well, I need a conversion factor. SO2, 16 times 2. S. I need to check. Sulfur, 32.1. 32.1. So 32 plus 32.1, 64.1 grams per mole. So 2.5 grams, 64.1 grams per 1 mole. All right? So what do we get there? 2.5 divided by 64.1 equals 0.0390. I'm going to keep an extra digit and we'll round back. And that's moles of SO2. All right, so now what are we going to do with that? Well, for every 2 moles of SO2, I'm going to get out 197.8 kilojoules of energy. So why don't we just create a conversion factor out of that? 0.0390 moles of SO2, and for every 2 moles of SO2, I'm going to get 197.8 kilojoules of energy. Moles of SO2 are gone. And now I'm going to take that number and multiply by 197.8. And I am going to get negative 7.7 kilojoules of energy given off when 2.5 grams undergoes that reaction. So now we've completed it. we've completed our stoichiometry with energy, because we can now go from mass and then out to energy we predict to get out. All right, this isn't calorimetry. This is what we predict to get if we know this thermochemical equation to be true. Write a balanced chemical equation whose energy change is the molar enthalpy for combustion of hexane. Well, again, if it's molar, all that it means is that we need a coefficient, right? We need a coefficient of 1 for hexane. In order for you to do this, you need to know what hexane is. Hexane is C6H14. So we're simply writing a balanced chemical equation such that the coefficient for the hexane, C6H14, is 1 because it's molar. So plus O2, CO2, H2O. And you know what? We've been leaving this as 1 for a long time, since we started doing stoichiometry. 6, 6, 14, 7, 6 O2s, half of 7 is 3.5, 9.5 O2s, and we leave that guy as a 1. We don't write it in, but there it is. That's a terrible 1, as a 1. And that right there is the reaction that represents the molar enthalpy for hexane. All right? So it's really just manipulating our equations. So there you have some homework that you can do to practice thermochemical equations.